So hello everyone, this is Sia from Microsoft. Today I'm going to present a way to prevent programmatic focus in iframe. So currently there is no way to prevent iframe from taking focus away from the main frame. If element of focus is caught inside the iframe, then the focus can be stolen without the user noticing, which is a security concern. As shown in this demo, like I'm typing my username and password in the main frame, and suddenly the focus is jumped into the iframe, and now I'm typing my password into the iframe, and my password is revealed and leaked. Another motivation is to improve the keyboard accessibility to host in the hosting web app. Like when user navigate the host app using the keyboard, the embedded iframe can take the focus, which breaks the keyboard navigation in the hosting app. And there is a proposal to the problem, which is introduced a feature policy called focus without user activation. The feature policy is used to block the focus change without the user activation, and the default is set to block programmatic focus in third-party context. The GitHub issue was raised in the Web App Security Working Group and WWG like 5 years ago. There was also HTML spec PR open, but unfortunately, it was left open because of some unanswered questions, like what should be the default value? Should we block the third-party context to get programmatic focus by default? And the next question is, should we allow focus delegation? Like the parent frame can call iframe.focus and pass the focus down into the iframe with this feature policy set. So we revived the discussion like a few months ago, and luckily we got this issue discussed in the TPAC 2024. And I'm happy to say that all the unknown questions are answered and the issue is resolved. So we got a green light. There was a Chromium CL landed several years ago. The CL introduced the feature policy into Chromium and hooked it up to document.isFocus allowed helper function. The current implementation is behind the runtime feature flag. However, there are still few gaps. Like for example, the current implementation, the default is enable for all. We should change it to enable for self. And the next gap is that there's missing focus delegation logic. And also there's some implementation bugs, like user can no longer tap focus into the iframe if this feature policy is set. So for next steps, besides the web standards work to land the HTML spec PR and start a tag review, we should definitely resolve all these gaps in Chromium and hopefully ship. And that's all. Thank you.
Hi, everyone. I'm Aoyuan from Google. And today I want to talk to you about third-party script and page performance. So for web developers who care about page performance, often a big problem for them is long tasks injected by third parties. And these long tasks are often out of their direct control and hard to improve. So that's why knowing how a third-party technology performs beforehand is crucial. And that's why we start working on detecting them. Well, thanks to long animation frame timing, or LOAF, which help exposes details on event loop that run long on main thread. And these details not only include timings, but also script information, which provides us the capability for detecting third parties. And we have achieved that by doing regex matching on the source script URL. Detection. We're now able to detect third-party contribution to LOAF in both chromato traces and UKM. And here's an example of the chromato trace slice. If you zoom into one of the long animation frames being captured, you may find the script execution block that is in dark green. And the details of it shows the third-party technology is being categorized into, here in this example, it's WordPress, and it's invoker type, which is event handler here. Types. We define 6 different types in traces and 2 different types in UKM. And these types are important because they help you understand the way how the script is slowing down your page. Technologies. We currently support 16 different technologies, including YouTube, WordPress, TikTok Pixel, Meta Pixel, extra. And this is just a first patch after prototyping, and we aim to add more in the future. Limitations. This feature highly rely on regex pattern match. So the patterns are not exhaustive, and there could also be false positive case. And if the script being pre-downloaded and served by the first party, then we are unable to detect them. There's also a limit on the number of technologies we can support because there's always performance overhead that comes with it. Well, this feature has been launched this year and it's now in stable. Give it a try and let me know. Thank you.
Matthias?
Hi, my name is Matthias Overty, and I work on Google on the web platform speed tooling team. I just wanted to highlight a few things that our team works on in terms of looking at speed in the wild. So we aim to provide tooling and guidance to teams to understand and improve performance. And we mostly focus on the 3 core web vitals. So just as a quick reminder, that's largest contentful paint, which measures page loading performance, interaction to next paint, which measures interactivity, and cumulative layout shift, which measures visual stability. And all of these are measured on user devices. So we end up looking at 3 different elements with those. So first of all, we do alerting. So when page load timings kind of differ significantly from what we expect the page load timings to be, we get an alert and bug filed, which is something that we can investigate. And then some of these end up being related to, for example, holiday effects, like people browsing different web pages around Christmas than they do the rest of the year. But there's also other ones that, for example, flag performance changes in like A/B experiments. And the next one is so A/B experiments. So feature teams can run an experiment, and if there's changes in, for example, any of the core vitals, we can kind of help them investigate and understand the size of that regression. And finally, profiling. So we do statistical profiling based on snapshots of the call stacks, and we can aggregate that across users to get insight into function call duration. We can use that to investigate issues as well. So finally, I just wanted to highlight a quick example. Recently, a team was trying to change the render frame host to align one-to-one with documents, and they noticed a regression in LCP. So we're able to look at the profiling data to look at specific function call durations and come up with some hypotheses on what could be causing that regression. So that's still ongoing, but as a next step, we also want to look at some other functions outside of the render frame host to see if there's any other functions that potentially regress and either identify them or rule them out. And that's it. Thank you.
Thank you. Johnny?
Hello, everybody. My name is Johnny Samek. I work on the Chrome team, and I'm going to talk a little bit about web platform telemetry. And as you probably know, we've been collecting various types of telemetry for a long time in Chrome, and I'm sure other implementation on Chromium do the same. But what we haven't been doing is to sort of collect that at the web platform feature level. As we heard earlier in the week from Kadir and James's talk on baseline, there's a effort undergoing in the WebDX community group right now to define what the feature set of the platform is, and we would like to have telemetry that kind of maps to that. And we already have a way to collect telemetry. Web feature and CSS sample ID use counters exist, and unfortunately the name web feature was taken by these but we decided that we want a clear sort of set that directly maps to the features that are being defined. So that's missing today. Chrome status exposes or shows the use counter data already, but what does a use counter mean in Chrome status? It's broad spectrum. Nobody really knows. May map to a feature, may not, may be some very specific measurement, etc. So we want to clean all that up. We now have a WebDX feature use counter type that is explicitly mapping directly to the feature set that's being defined by the community group. And what we want to count with those features is specifically when web developers use them, which is at times very tricky. There's overcounting, undercounting, etc., depending on feature detection or internal usage of code or whatnot. So it needs a bit of attention to get this stuff right. We want to also then expose these publicly, like we do for the existing use counters, but through the new platform or web status dashboard, probably Chrome status eventually as well. We have a target for this year that we're working towards, which is to both map the features that we've shipped in Chromium since 2020. We want to add telemetry for those. We're also asking going forward that all features are going to have one of these new WebDX feature use counters so that we can maintain this over time and get this available publicly on the dashboards. And the ask is basically for any new features that you all are working on, add these new web feature use counters. They're exactly the same as the existing use counters, just different namespace. There's a WebDX feature Mojo file that has details around naming and all this stuff. There's still some tooling that we could use to sort of maintain that and make sure it's correct. We're working on things like that still. And then we're obviously also looking to get contributions to the actual definitions as new features are being developed. It's a bit of a chicken and egg problem. We won't have definitions for features that we haven't really defined yet. So that's something we'll run into. The documentation in the Mojo file talks about that a little bit. And we also, of course, want mapping of web platform tests to new features. So that's something you can contribute. Well, look at that. And there's a tracking bug and a burn down sheet. And thank you very much.
Thank you, Johnny.
Yeah, I was planning on trying to brush right up on the gong time, but Johnny beat me to it. Thank you, Johnny. So hello, my name is Daniel Smith. I work on the interop tooling team at Google, and I'm going to talk a little bit about what's new in Chrome status, which is the official tool used for tracking the feature launch process in Blink. So we've been working to make Chrome status the central hub where feature owners actually request the creation of an origin trial. And there are a lot of prerequisites that come along with creating an origin trial. Some of you may be familiar with this list here on the left. Well, now on the origin trial creation request form, we have additional checks that actually go and make sure that your Chromium code changes have actually landed as you're submitting your origin trial creation request. Now, Chrome status is actually fully integrated with the origin trial creation process. So whenever you submit your approved request, it will be automatically created, and your trial will be ready for trial participation within minutes. So if your origin trial start milestone is supposed to come at a later branch date, your trial will be activated on that branch date. We also have the capability to post intents directly to Blink Dev from Chrome status. So on any of the intent draft pages, there's a button on the right. If you click that, you'll be prompted to add any users that you'd like to CC in the intent thread, and that will post the intent directly to Blink Dev, and your discussion will be ready shortly. On the detail page of a feature, we also have, for any GitHub issues that represent external reviews, they will now display even more information at a glance. So any closed issues will display the resulting position, and any open issues will display the amount of time in which they have been open. And then, of course, hovering over these links will also give even more information at a glance. And as you can see here, Mozilla seems to be excited and positive on my BlinkOn presentation, which may or may not be their official stance, but is great turnaround time. So, and finally, yeah, Chrome status is always a work in progress, and we're trying to integrate to make the data that's within it as accurate as possible, but also to make the tool as easy to use for feature owners and API owners as well. So if you have any suggestions, we'd love to hear about it. If you have anything you see that would make your life easier, please send us a message or open an issue. We'd love to hear from you. And I think I might be close, but I want to thank my team also.
I'm Andre. I've been looking at generated bindings performance for the past few months. I'd like to share a few insights and show you a couple of snippets of code. And as it turns out, some web ideal features may be not as efficient as we'd like them to be. So first of all, the disclaimer that most of the time what I'm going to tell and show isn't really relevant for the majority of APIs. It only makes sense in really small fraction of APIs that are hard code, like called frequently, and do the actual work relatively fast so that the bindings overhead is significant. So like maybe if you're working on the next payment API, you can disregard that. If you're working on some graphics or audio video processing, give it a consideration. So first of all, let's talk about unions. This used to be a little bit simpler back in the wild days of handwritten custom bindings, where we would just take a weight value and iterate over possible types of that value. These days, we introduce a C++ type, and which effectively makes us dispatch of all the possible union types twice. First, when we, on the binding side, produce that type, and then when the actual C++ implementation uses it. And then you can see there's also a heap allocation here. So you can figure out we're pretty desperate for bindings performance at this point if we're talking about things like that, but it actually pops up occasionally on the profilers. So next to the next kind of favorite way of implementing polymorphism, which are overloads. And like this is a bit of an outlier, but you can see there are like 17 different overloads here, and it may take as many as 12 checks to actually get to the implementation method. And those has instance check, by the way, aren't free. So again, it doesn't matter in this case of this particular method because it's relatively expensive on its own, but sometimes for simpler method it does. But then sometimes overload dispatch can actually be fast, and this brings us to no alloc direct call, which is often misunderstood extended attribute because, well, there are a couple of good reasons it's misunderstood. First of all, it's not a direct call. We still generate the binding. And second, allocs are actually fine. So we fixed it, and you can do heap allocs, re-enter V8 if you want. There's still some penalties, and there will be binary size penalty because we're generating all the new way. And also it really works for simple numeric types. Either we get as V8 value and we'll do our usual conversion magic. But the good news is that V8 knows the types, and presumably, like for the compiled code, at least V8 would be able to dispatch it instantly to the right overload. And then the last thing is a sort of a workaround for the cases of unions when all members of the unions can be cursed to single representation, which is often the case of buffer source-like types that are widely used in the specs. So those can be, as long as they're just arguments to a binding call, sometimes all the call wants is basically a span of bytes. So they can be passed as that. This results in basically in actual span being passed. And this also works for typed arrays and their JavaScript equivalents of the same type. That's all I have.
Mike's just feeling himself on that gong now. Yeah.
Good afternoon. This is Yunshi from AG Electronics. I would like to talk about updates on spatial navigation in Blink. Spatial navigation navigates web page with direction keys such as keyboard and remote controller, and you can refer this presentation in detail. Instead, I will focus on what is updated. So many spatial navigation issues were reported, but not updated for several years. So LG team improved in this year, started from 27 issues and resolved 14 issues. So there are 3 major changes. So first one is we improved flaky web tests. Previously, 31 tests were flaky and excluded from web tests. Now most tests are improved and only 1 test is excluded from web tests. Next one is we improved reachability to focus of element on page. So there are 2 example cases. So first case is overlapped element. So in this picture, B and C are overlapped. And when press right key started from A, then C was not able to get focused. But after improved, C can be focused. And next example is contained element. So as you see in the picture, C, when C includes B and C have same height and left position, and B is defined earlier than C, and press the right key from starting from A, then previously C cannot be focused, but after improvement, C is able to be selected after A, and then B and D are selected. Last item is we fix buggy behavior in specific case. So we fix the scroll issue for focused scroll of element with specific zoom level. So with specific zoom level, so scrolling down and right cannot be completely done. But after fixing the bug, scrolling down and right can be done completely regardless of zoom level, and right and bottom can get focus. This is the end of my presentation. Thank you.